Hello friends, today I am going to talk about applications of Schrodinger equation, potential barrier problem and hydrogen atom. This is a potential barrier problem and you see how potential is varying with x. Now, in region 1 Vx is equal to 0 when x is less than 0, in region 2 Vx is equal to V naught when x is between 0 and a, and in region 3 Vx is equal to 0 when x is more than a. Particle with energy E is incident from left and we are going to consider two cases. Case number 1 when E is less than V0 and case number 2 when E is more than V0. That means, in one case the energy of particle is less than the barrier height and in another its energy is more than the barrier height. Now, we apply quantum mechanics when E is less than V0. Suppose phi 1, phi 2 and phi 3 are solutions of Schrodinger equation in region 1, 2 and 3 respectively. We have already seen how to write Schrodinger equations. So, we write the equations for phi 1, phi 2 and phi 3, and what you see are these three equations, and here we have defined rather two variables k square and k1 square. K square is 2m by h bar square multiplied by E and k1 square is 2m by h bar square V0 minus E, and as I have told you V0 is more than E. So, both k square and k1 square are positive. Now, we go about and try to find the solutions of these equations, and we note that in region 1, in region 2 and region 3 we write the solutions phi 1, phi 2, phi 3 as you see on the top three lines. You notice that physically A times e to the power I k x and B times e to the power minus I k x are incident and reflected waves in region 1, and capital E times e to the power I k x is transmitted wave in the region 3. Now, you must notice that I have written for phi 1 and phi 3 oscillatory solutions and I have written exponential solutions for the region phi 2, and then from these variables I find the incident probability current density J I in the region 1 and reflected probability current density in the region 1, both in the region 1 G I and G R, which are incident and reflected probability current density. In the earlier series I told you how to write these J's, and just by the simple applications we can get these expressions. Now, J T, that is the transmitted probability current density, is written as k times mod of E square. Now, you define two coefficients, reflection coefficient R and transmission coefficient T. R is J R by J I and T is J T by G I, that is they are ratio of reflected and transmitted probability current density to the incident probability current density. So, you can easily see that R is mod B square by A square and T is mod E square by A square. Physically they are measures of fractions of incident flux of the particle which is reflected oblique transmitted by the barrier. Now, we have one more thing, that phi 1 and phi 2 and also the derivatives must match at x is equal to 0, and similar arguments hold for phi 2 and phi 3 at x is equal to a. So, we obtain 4 equations involving parameters a, b, c, d and e, and these can be solved for b by a, c by a, d by a and e by a, but we need only b by a and e by a for r and t. Now, continuity of phi and d phi by dx yields these relations as you see on the slide which involves A, B, C and D. Now, express A and B in terms of C and D using first two equations and express C and D in terms of E using last two equations, and then A and B both can be expressed in terms of E. Now, somewhat tedious but straightforward calculations yield these expressions for R and T. These expressions you are seeing on the slide, and these expressions involve sine hyperbolic k1a, and k1 is the parameter I have already introduced, and you see that R plus T is equal to 1, that is sum of reflection coefficients and the transformation coefficient is 1 as it should be. Now, we discuss these relations, and classically T is equal to 0 whatever is E as long as E is less than V0, because if energy is less than the potential barrier height, then it will not be able to cross the barrier as far as classical physics is concerned. But quantum mechanics tells us that T is equal to 0 when E is equal to 0 and T tends to 1 over 1 plus m V naught A square by 2 h bar square as E tends to V naught from below, always keeping T less than 1. Now, what is important is T is not equal to 0 even if E is less than V0. So, quantum mechanically the particle manages to cross the potential barrier V0 even with insufficient energy E. So, it is as if laws of quantum mechanics allow the particle to tunnel through the barrier. Hence, transmission with E less than V0 is called tunneling effect. Now, consider another case when E is more than V0. You see the slide here, and here the particle is incident with energy E which is more than V0. Now, Schrodinger equation for phi 1 in region 1 and phi 3 in the region 3 remains the same, but equation for phi 2 in region 2 becomes del 2 del x 2 plus k 2 square phi 2 is equal to 0. Now, k 2 square I have defined as 2 m by h bar square E minus V0. Remember, E is more than V0, so k 2 square is positive. Now, please note that the parameter k1 used in the case E less than V0 now goes over to the parameter iota k2 in the case E more than V0, where iota is square root of minus 1. This is a thing to remember and to take note of, that is k1 from the case 1 has gone over to iota k2. Now, the continuity of phi and d phi by dx at x is equal to 0 and x is equal to a give us these four relations as before. You see these relations on the slide, and armed with these relations we can compute R and T as we did for the case E less than V0. I have written down these four equations, and these four equations are just the continuity conditions on phi and d phi by dx at the 2 points x is equal to 0 and x is equal to a. Now, we need not do the whole exercise again. We have already noted that parameter k1 when E is less than V0 goes over to the parameter iota k2 when E is more than V0. So, what we can do is we can write down the expressions for R and T in this case from those of R and T in the earlier case by the replacement k1 goes over to iota times k2. So, sine hyperbolic k1a goes over to sine hyperbolic iota k2a, and it is iota times sine k2a. With these replacements we can write down the expressions for R and T, and again we note that R plus T is equal to 1, but remember and you see that sine hyperbolic squares have gone over to sine squares. Earlier we had sine hyperbolic square k1a, now we have sine square k2a. Now, another thing to note here is that for some values of E, T is equal to 1 when K2A is A times root 2m E minus V 0 by h bar is equal to n pi, where n is equal to 1, 2, 3. Because for these values of K2, your sign term becomes 0 and then T becomes 1. What you see here is variation of transmission coefficient with energy, and you note that when E is less than V 0, T is not equal to 0, contrary to classical physics, and when E is more than V 0, T is not always equal to 1, again contrary to the classical physics. Only thing is that for some value of E, T is equal to 1, as you see on the slide, but then it brings to the fore very important difference between classical physics and quantum physics, that where we expected T is equal to 0, it was not 0, and where we expected T is equal to 1, it was not equal to 1, and this whole variation is depicted in this graph which is before you, which is T versus E by V 0 graph, and this tells the difference between classical physics and quantum physics. Now, tunnel effect provides explanation for these things: emission of alpha particles from a radioactive nucleus, tunneling current in a scanning tunneling microscope used to study metallic surfaces, nuclear fusion in the sun where a proton tunnels the potential barrier provided by another proton, liberates energy by fusion and makes life possible at planet Earth. This is the diagram you see, which is the potential seen by alpha particle in a radioactive nucleus. What you note here is that the barrier is not just stepwise, but it is of the shape that you see here, but again the essential physics remains the same, that is a particle has to cross this barrier when E is less than V 0. Now, we come over to another problem, which is the hydrogen atom problem. Now, what is a hydrogen atom in the first place? Essentially, it is just a proton and electron system where electron is orbiting around proton and the necessary centripetal force is provided by Coulomb attraction. Classically, electron is orbiting around proton, and then the centripetal acceleration of electron should make it lose its energy and make it fall into the proton in about 10 to the power minus 12 second. See, 10 to the power minus 12 second, such a small quantity. In so much time, we expect classically that the electron should fall into the nucleus, but then we know that the atom is stable. Further, classical model is not satisfactory because it does not explain spectral lines emitted by hydrogen atom. Then came on the scene Bohr, and he gave Bohr model of hydrogen atom with the following assumptions: electron revolves only in certain orbits of radius r with velocity v such that quantization condition mvr is equal to nh bar, where h bar is h upon 2 pi and n is 1, 2, 3 holds. Now, these n's are just called quantum numbers, and with this condition the energy E n of the nth allowed orbit becomes E n is equal to minus 13.6 upon n square electron volt. Minus simply means that the electron is bound. You have to give that much of energy to make it just free. Now, energy is absorbed or emitted when atom makes a transition from one allowed orbit to another allowed orbit. Emission of different spectral lines is due to different n to m transitions with the emission of radiation with the frequency nu is equal to E n minus E m by h. Now, Bohr model was successful in explaining various spectral lines of series Lyman, Balmer, Paschen, etc. in the spectrum of hydrogen atom. You see, Bohr model is one step further from the classical model, and it explains so many things about this hydrogen atom which were not explained by classical physics. But then there are some weaknesses of this Bohr model, and about these we can say that assumption of only certain allowed orbits which are non-radiating and stable is ad hoc and not supported by more fundamental theory. This is a very serious problem with the Bohr model. And then further, well defined circular orbits violate uncertainty principle of quantum mechanics. Definite trajectory means knowing position and momentum simultaneously with absolute precision, and this is what is not allowed by uncertainty principle. So, the very concept of orbit is not consistent with quantum mechanics. So, proper quantum mechanical treatment of hydrogen atom is required, where all information about it should come from the wave function. I have already told you before that in quantum mechanics, what you need about the wave function and all information about it will come from the wave function. So, when we try to find the wave function, we have to solve the corresponding Schrodinger equation. So, we go about writing the Schrodinger equation for hydrogen atom. Hamiltonian operator is H operator is p square by 2m plus V, that is the potential, and P is equal to minus H bar del, and for Coulomb potential V is minus E square upon 4 pi epsilon 0 r, that is the Coulomb potential. So, armed with these we write the Schrodinger equation, and now it is useful to work with the spherical coordinates r theta phi instead of Cartesian coordinates x, y, z. Ultimately, both r theta phi and x, y, z gives you the position of the particle. So, Schrodinger equation in spherical coordinates becomes this that you see on the slide, and then in quantum mechanics you note that x and p are not well defined simultaneously because corresponding operators x hat and p hat do not commute, that is x p minus p x is equal to iota h bar I and is not equal to 0. So, this is a very fundamental issue in quantum mechanics, that we have non-commuting operators. X and p are examples of non-commuting operators. Their commutator x p minus p x is not equal to 0. That means, we cannot define them simultaneously. Now, what happens in hydrogen atom? Here the set of commuting operators are H, that is Hamiltonian, L square and Lz, where L is orbital angular momentum. L square is the squared of angular momentum and Lz is z component of angular momentum. Now, the possible values of L square are eigenvalues of the corresponding operator L square, which are L into L plus 1 h bar square, and L takes the value 0, 1, 2, 3. So, this small l is another quantum number which is introduced in hydrogen atom problem, and small l takes the value 0, 1, 2, 3, and then the possible values of Lz are eigenvalues of corresponding operator Lz operator, which are m h bar. What about m? For a given L value, m takes 2L plus 1 values from minus L to plus L with the interval of unity, that is m is equal to minus L plus 1 up to L. For example, if L is equal to 1, then m will take 3 values minus 1, 0 and 1. Now, wave function psi is product of angular part called spherical harmonics, which is ylm theta phi, and the radial part r, and then these spherical harmonics are well defined and obey normalization condition as you see on the slide, and then the radial part also satisfies the condition as you see on the slide. Now, this is important that radial part r should be well behaved throughout the space. This is a must for radial PR to be well defined everywhere, and the condition of good behavior on R leads to emergence of quantum number n, where n takes 1, 2, 3 values and En is equal to minus 13.6 upon n square electron volt. So, this n has come just because of the fact that we have imposed definite conditions on R. Radial part now depends on quantum number n and L, and the psi n Lm is now product of R and Y Lm. The degeneracy of psi. Now, we can show that degeneracy of psi is n square. What is degeneracy? It simply means that there are many possible Lm states for a given n having the same energy En is equal to minus 13.6 upon n square, and this degeneracy is doubled when we consider spin variable. These are the some values for n and electron and R for different values of n, 1, 2 and 3. Here is the variation of radial probability density for 2s and 2p states. You see, the idea of orbit has gone over to a distribution. Now, the electron is not in a particular orbit, but it is distributed throughout the region. Now, you talk of angular distribution of the p states, px, py and pz. Out of 3 states y10, y11 and y1 minus 1, we can construct 3 other states whose angular distributions are proportional to cos theta, sin theta cos phi and sin theta sin phi. And we have some lobes like structures, and we call them px, py and pz orbitals. You see these orbitals in the diagram, px, py and pz. Px has 2 lobes along the x axis and similarly py and pz. Spin quantum number. In addition to orbital angular momentum, quantum mechanics permits spin angular momentum whose z component takes only 2 values, ms h bar by 2, ms is equal to plus minus 1. For each NLM set, there are 2 states corresponding to ms is equal to plus minus 1. So, the degeneracy of states with energy En is equal to minus 13.6 from n square now becomes 2n square. So, armed with this, we say now that the wave function is psi n L m and together one more quantum number ms. Together these define the quantum states of a hydrogen atom. So, friends, we have seen how laws of quantum mechanics allow a particle to tunnel through a potential barrier, and then it also explains the fusion reactions in the sun. Also, we have seen how quantum mechanics gives a better model of hydrogen atom compared to Bohr model. I hope you enjoyed the lecture. Thank you.